All right. So first, the tools we need to like finally build up to questions about confidence intervals are that we need to know about normal distributions and what the CLT says. Using those together, we can, do confidence interval questions. We also need Chebyshevs, but like I'll cover that later. So uh, the actual formula for the distribution of the normal is not as important as like what it like how it's sort of used, because the important thing is that all normal distributions are shifted and scaled versions of the standard normal. And this standard normal means it has the expectation 0 and variance 1, or standard deviation 1, same thing. So here's like a very short, not really a proof, like a sketch of why they're all shifted versions. So suppose we have like a normal distribution with some mu and some sigma. Then if we subtract away mu, it's going to be centered at 0. And if we divide out the sigma, it's going to turn into a standard normal. So we can also write it as mu plus sigma times x tilde, where x tilde is the standard normal. And similarly, like for any constants a and b, we can always write it as like a shifted and scaled version of the standard normal. The CDF of the standard normal is like not, it's impossible to integrate. So we use this special like phi function to denote it. And this will capture like the probability that the standard normal is less than or equal to some cutoff, like this cutoff A. And like in problems, you'll probably need to write stuff in terms of like the inverse CDF. All right, so now moving on to what the CLT actually says. I'm going to start by saying it in English and then like gradually add more and more math, if that makes sense. So in English, the sum or average of a bunch of ID variables approaches a normal distribution. So in math, let's give names to our ID variables as well as their sum. So let x1 through xn be IID, where each of them has expectation mu and variance sigma squared. Then their sum, which is like, x1 through xn, converges to a normal distribution. But like what normal distribution specifically? For that, we need to compute expectation of the sum and variance of the sum. So does anyone happen to know what the expectation of the sum might be? You can put in the chat or say something. Okay, I'll start out by all right, so the expectation of Sn is going to be the expectation of the sum of all of these. And by linearity, this is going to equal like the sum of their expectations. Now, we know that each of the expectations is mu. So if we keep going, like we get n times mu. Now for the variance. So, oops. So the variance of the sum is going to look something like this, where we can actually still use the additive property, but for a slightly different reason. We don't have to take into account any of the covariances between xi and xj, because they're IID, which means they're independent, which means the covariance is 0. But because the covariance is all 0, the variance of the sum is the sum of the variances. And then that turns out to be n times sigma squared. All right. So now we see that Sn will be a normal distribution where the expectation is like the expectation of Sn and the variance is the variance of Sn, because like that's what you would expect it to approach. So, well, what are these specifically? We just found these values, so let's plug them in. This is going to be exactly normal of n mu and n sigma squared. So this is like the mean, and this is the variance of Sn. And now, like, to make it look like the form in the notes, we need to shift it and scale it appropriately. So like I did in the part right above here, I first subtract away the mean so it's centered at 0, and then divide out by the square root of the variance so that the variance gets like squished to 1. Plugging these all in, we get n mu here, and square root of n sigma squared here, which simplifies to square root of n times sigma. And then this approaches a normal distribution, and this is exactly what note 17 says. All right, are there any questions? For those of you who came late, in Berkeley time, I'm just giving like a quick review of like everything up until confidence intervals. Okay, then I'll move on to the next the next part, like defining what a confidence interval is. So a confidence interval is always like you're trying to estimate something. The thing we're trying to estimate, I'm just gonna call it theta here. And it's gonna have significance like 1 minus delta. The reason it's 1 minus is because like you might want like a 95% confidence interval, but your delta is actually going to be 5%. Like you want the chance that's wait, you want the chance that it lies outside the interval to be 5%. So yeah, that's sort of why it's delta. Okay. Alternatively, you want it to lie inside the interval with like the pretty high confidence, which is like 95% or 1 minus delta. Okay, so this is small. Delta is small, which means like the overall confidence should be like pretty close to 1. All right, sorry about that. So the whole point is to make this thing true, and we can do that using either Chebyshev's or inverse CDF of the normal distribution. Okay, so more like in more equations, I guess, you want to bound the probability that it lies outside the interval to be less than delta. But by Chebyshev's, it's also less than this. So really we're trying to use both of these to like the thing we're trying to solve for is like this thing, and we want to solve for the width of the interval, which is like epsilon. Oh shoot, okay, sorry. We're starting at like 8:10, but in Berkeley time I'm giving a review. Okay, so I think this is wait, oh shoot, okay, there's one more approximation you can use, which is the normal approximation. Uh, sorry. CLT can be one-sided or two-sided. So okay, something like this. All right. Okay, I guess I'll wait a minute or so for more people to trickle in because like Berkeley time has just started. When do we set delta equal to Chebyshev's and when do you set it as greater than? Just depending on the question format. Yeah, pretty much. Because like the inequality goes in one direction. Like you can make your interval wider, so then it will still be less than like the stuff at the edges is going to be less than delta, but you usually want like the narrowest possible interval, in which case would be inequality in an equality. How often do we use a different estimator for a CLT or Chebyshev bound? Do you mean like what we're trying to estimate or?
Oh no, like the 1/n times the sum of the random variables.
Oh, okay. So the thing is like this actually falls right under CLT. Like if instead we were trying to estimate 1/n times the summation, then you would just go through and set like 1/n times Sn is going to be blah, blah, and you repeat the whole thing. And like the proof is almost identical. But like your normal distribution will look a little bit different because this time you'll be like expectation of 1/n times Sn and variance of 1/n times whatever.
So how often would we have to like change our estimator then? Like instead of using 1/n, like let's say we use like 4/n or something.
Oh, that depends on the problem. So I don't think I can give like a all or nothing answer.
Oh, okay, I see, I see.
Okay. And then for normal approximation, like, okay, this should also be like centered, like this should be times say times sigma. But the idea here is that like you want to try to fit x minus theta all over sigma to an approximate normal distribution. So if you like rearrange it and write it this way, then it'll be like inverse CDF. So whatever your answer will be, it'll be in terms of like the inverse CDF of some cutoff. And usually you'll be given the cutoff, or you can solve for it. Okay, so okay, sorry, let me just send one more time in the chat the CLT handout that so you can follow along. And then we'll start by doing some questions. So from the handout, there's like 3-ish types of questions because well, given the CLT and just like the general structure of the confidence interval, like you can solve for delta, you can solve for epsilon, you might sometimes have to solve for n, which is the number of samples you need. So those are like the 3 different types of questions. Either you find the width of the confidence interval. Okay, the width is like a little bit misleading because uh epsilon is technically like, I guess it's like technically half the width because it's the distance from the center to one of the edges. So it's technically 1/2 the width of the confidence interval. And another type is like you might want to approximate a probability with some confidence that you want to hit. And then also, oh shoot. And then, sorry, the last one is like you want to find the minimum number of samples to hit a certain confidence and to estimate some certain thing. Should this be 1 over sigma c sigma instead of I think it should still be C because like if you rearrange, like this is gonna be approximately normal. So if I like just rearrange by putting the sigma here, this is gonna be like uh inverse CDF of C. So maybe I should have written it more clearly. Okay. So I'll give you like 2 minutes to read the first question, which is we're trying to find the width of this confidence interval. And this is like the first question that TC has on his handout. I'll also write it here. Okay, so if you're curious about why this is 350, a 6-sided die has like expectation of like a roll of a 6-sided die, a fair 6-sided die, is 3.5. So the expected roll of 1,000 rolls would be this times 1,000, which is 350. So right away we see that this is like the expectation of the sum.
Isn't 3.5 times 1,000 3,500? Or am I?
Wait, oh shoot. Oh, oh shoot, you're right. This should say 100 then. Sorry.
Okay, thank you.
Yeah, no problem. Thanks for the catch.
When is n big enough to use normal instead of Chebyshev?
Well, according to AP stats, I've heard like 30 is roughly the threshold. But like if the question says use a normal approximation, then you can assume n is big enough.
Thank you.
All right. So just by looking at like the trade-off, like either you win the 3 times the ticket price or you lose the ticket price. Does anyone have any ideas on what we should pick our confidence or delta to be? Or our confidence is 1 minus delta, but like, are there any ideas on like what kind of confidence level we should pick? And as like a hint, how often do you need to win to make money in the long run? Yes, you need to win 1/3 of the time. And the reason is because like 1/3 you win like 3 times the price, and the other 2/3 of the time you lose the ticket price. So win 3 times ticket plus 2/3 of the time you lose 1 ticket. So this would be like ticket price times like, well, 1/3 times 3 plus 2/3 times, wait. Oh shoot. If you win 2 times the ticket price, you actually like, you only, like your profit is only 2 times the ticket price because you need to like pay anyway. So this becomes 0.
Since this is saying that you run the casino, wouldn't that mean that it should be the other way around, actually? Like you should win 2/3 of the time? No. I mean, it's fine. It's probably like,
Oh wait,
be
you're
like
right.
the
Yeah,
inverse of it, but
yeah.
yeah.
Yeah. And the rest of the problem, like you want, or I'll just say casino, want casino to win 2/3 of the time. Well, at least 2/3 of the time. And the reason is because like this is the break-even point. All right. So now we have our confidence level. We have our expectation here. We also have what else? We have our n. So putting all these pieces together, we can start building a confidence interval. All right. Why can't we? I have a question that says, why can't we just make b equals 0? That is true, but we want to make it like as tight as possible to make like the customers think they have a chance or something. Just like in confidence, like generally in confidence intervals, you can make the interval wider, but you want the narrowest possible interval so that like I don't know, it's as tight as possible. All right. How do I get 1/3? How do I get from line 2 to line 3? Oh shoot. Okay. So okay. So you still like pay one price minus 1 times ticket price. So like 1/3 of the time you win back 2 times like the price, and 2/3 of the time you like win back, well, -1 times. So like this cancels out to be 0 in the long run. All right. So let's like try to set up a skeleton of what this should be. Well, I'll just write it as Sn because it makes it easier. And then 350. All right. So we have like a bunch of, we have, well, 2 blanks to fill in. Does anyone have any ideas on like what maybe are like what we should put in either of the blanks?
Should we put V in the first question mark?
Yes.
And then like 1 minus the what? No, wait. Shouldn't it be flipped around or no?
Oh shoot, you're right.
So like greater than or equal to 1 minus delta.
And we want the chance of UI within the interval to be, wait, 1/3. Okay. Oh, the reason it's 2 times is because like even if you win, you still have to pay the original ticket price. So like your pure profit is like just 2. Okay. So now we're like ready to solve. We can either use Chebyshev's or the normal approximation.
Wouldn't CLT be better here because like we have like 100?
Yes, exactly.
Yeah.
So now we have to like center it so that you can put it in terms of the normal, the standard normal. So if we sort of scale everything down, the probability that this is the same thing as oh shoot. Let's first figure out all the pieces. So the expectation is 350. What would the variance be? So that'd be like 1000 times the variance of one dice roll. And then like this turns out to be, oh boy. You can bash out the e of x squared minus e of x thing squared. But what I have down is that the variance is 35/12. This is a relatively small calculation, so I wouldn't worry too much about it. All right, so if we plug into our CLT approximation, then Sn is going to be roughly normal with 350 and 35/12, which is the same thing as saying Sn minus 350 over the square root of this is roughly the standard normal. Oops, yeah, it's 100. Wait, it's not 100 squared because, wait. Yeah, it's not 100 squared because like it's the sum of 100 variables. It's not like literally 100 times the one dice roll.
Isn't SN 100 times one dice roll? Isn't there 100 dice rolls? So SN is the sum of 100 dice rolls.
So like that'll be variance of like x1 plus blah 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 plus x100, right?
Yeah.
But this is not the same thing as saying 100 times x1.
But if all the dice rolls have the same mean and are equally distributed, then it's the same as 100 times the.
Yes, it's
roll?
100 times the variance. It's not 100 squared times the variance.
Oh, okay.
Oh, sorry. There's a couple questions in the chat. All right. So now that we have our normal distribution, we can, sorry, I have one more question. How do we calculate e of x squared? Well, for a dice roll, you can do like 1/6 times like 1 squared plus 3 squared. Sorry, 1 squared plus 2 squared, blah, 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 all the way to 6 squared. And then you subtract away the average squared. Like it's a relatively like, small calculation, so don't sweat it. Okay. So now we want to fit our like confidence interval into this normal approximation form. So we want Sn, how to write this? 350 away. So it'll be like this. Sn is going to be between 350 minus V and 350 plus V. How do I get E of X? The expectation of a dice roll is like 1/6 times like 1 plus blah 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 plus 6. which turns out to be 3.5. Uh, and then wait, why does it say the probability is less than 2/3 when we want to be less than 1/3? Oh shoot, I might have flipped the direction of the inequality. But like this is the one that will let us use Chebyshev or normal. Yes, I did work the variance out beforehand, so don't worry about it. Okay, so now we can sort of shift this sort of thing. First I subtract away the mean so that like it's centered at 0. And then I want to divide by the square root of the variance. So that would just be like divide everything through by square root of this. And then this is negative. So now we want to look up in our CLT table, whatever makes this, we want to win at most 2 at a time. Wait, shoot, I forgot. SN is fine because we want to measure whether the sum is more than V away from 350. Okay. And then now that we have this, we can, well, we can put everything into terms of like the standard normal. So this thing is going to have a distribution. Oh, sorry, this will have distribution standard normal. So to find this, we would do like CDF of this minus CDF of this is going to be this, right? Where did the 350 for the bound go? Oh, so when I subtract 350 from the middle, I also subtract it from both sides. Like the whole point is to get it into a form where the middle part is going to be a standard normal. Because once I have the standard normal, I can use inverse CDFs and whatever to figure out what V is. So in our case, the calculation we get is that to have a, wait, let me just draw it out. So if we want like 2/3 of the probability here, then each, like if this contains 2/3 and each of these is going to contain 1/6. So this means that like this probability should be less than 2/3, and to put it in terms of CDF of the normal, this would be like this cutoff is going to be 5/6, and this cutoff is going to be, wait, sorry. This is 1/3 and this is negative 1/3. Okay. And then like we want this to be less than sorry. This quantity will dictate what our V is going to be. So
shouldn't we be plugging in like V over square root of 35 over 12? Like that's our parameters in the CDF or no?
oh wait, shoot. Yeah, you're right.
Okay, thank you.
I want this to be less than 2/3. We can simplify a tiny bit more because like this is going to be 1 minus the other one. So this turns into, oh, this is like sort of by symmetry, because if this is one side, then the other side is going to be 1 minus that, because it's going to be that, but on the other side.
Wait, so why do we start with phi inverse instead of phi? Like just regular phi.
Oh, oops.
I'm sorry.
And then we finally we can multiply to the other side, and we get the v is less than this thing. If you're curious about the numerical answer, I believe it is 51.8-ish. All right. All right. Are there any questions?
So our estimator is just the sum here, not like the regular estimator we're used to using.
Yes. Oh, I have a question. Why is it 1/3 instead of 2/3? Oh, okay. Sorry, this was not super clear from the wording of the question. But like we run the casino. So if the customer wins 1/3 of the time, we want the casino to win 2/3 of the time. So this is a customer. And then this is like from the casino's point of view. Is phi of A the area to the right of A? Phi of A is the area to the left of A because it's the CDF. Why does the customer win 1/3 of the time? Well, we set our confidence to be 2/3. We want we as the casino want to win at least 2/3 of the time. So then that means the customer will win at most 1/3 of the time. Oh, casino wants to make money in the long run. So it turns out that to make money, the casino has to win 2/3 of the time. I thought Sn minus sigma root n over z. Wait. The root n and the n? Sorry, I'm not sure. I'm not quite sure what you mean. Okay. And also it's kind of hard for me to check private chat as well as write at the same time. So if you have questions, just put in the main chat, and like everyone else, if you can answer, please try to help answer. Otherwise, I'm gonna move on to the next one, which is like the second example out of 3, where we want to find the width to meet a certain meet this 95% interval.
So like if they're asking for like the width, would it be less than or equal to w like width divided by 2 or like something like that? Or
Oh, okay. So it should be defined in the question. Let me just quickly check which one this falls in. When they say width, they mean like the full thing. So like if this were your interval, they mean like the width of the entire thing.
oh, so we're doing like the absolute value then? We would want to make it less than or equal to w divided by 2?
Yes.
I see.
Although like it might be easier to set this, find one side and then multiply by 2 at the very end.
Oh, I see. I
Also
see.
know that this was in a separate semester, so that's why the notation is a little different. Why did we calculate the expected value of the 100 dice rolls and the expected profit? Yes. So at a high level, the reason we calculated the profit was profit gives our confidence. And then the expected value, this is 350. This lets us center our interval at the end. All right.
So when they say something like interval, you would just leave it as like epsilon, right? But when they say something like width, we
Yeah,
would.
you would want exactly the width.
Okay, okay, I see, I see.
How do you know you need to standardize the distribution? It's actually kind of hard to tell. But if n is like rather large, then you should try to use CLT. Otherwise, use Chebyshev. Here they specifically say CLT, so that means it's a normal distribution. I don't have the table, but we can leave it in terms of the inverse CDF. All right, just from like Poisson facts, the expectation and the variance are both going to be 2. So we can use those to find like the expectation of the sum and then use that to build our confidence interval.
This is just like a quick recap. SN approaches normal of its mean and variance, right? Or no?
Yes, exactly.
Okay.
This will also be on the first page, which I I can't really show both at the same time, but yeah,
It's okay, it's okay, it's okay. Thank you.
no problem. All right. So the thing that's going to be the thing that approaches the standard normal is going to be Sn minus E of Sn, which is 2n, all over the square root of like the variance of 2n, which is this. So this approaches normal of 0, 1. And this is what we should try to use what's it called? CLT on. Yeah. But in the question, we have that n equals 100. So we can plug in 100 like here and here. Okay. And we want to find we want the chance of finding meow to be at least 97%. So probably that meow is inside the search width is going to be roughly 97%. All right. So all we do now is we plug it into the CDF. So sorry. If it's centered at 200, then our width is going to be like it's like a width of W for the whole thing. So on this side it's going to be 200 plus W over 2, and on this side it's going to be 200 minus W over 2. So now we can, instead of just saying search interval, we can have it like this specific interval. If we rearrange a bunch of things, this is the same thing as saying Sn. Rearranging, we do the same thing. We subtract away the mean and then like center it. And I want this to be roughly 97%. So now that this middle thing is roughly normal of 0 and 1, we can again try to use like the CDF manipulations to eventually get to this. Okay. So this means that phi of this thing. I'm also gonna simplify this to say like 20 root 2. And this one also 20 root 2. Is roughly 97%. By using the same like algebraic trick as the last time, this turns into like 2 times this minus 1 is roughly 0.97. Algebra, the rest is like mostly algebra.
Is there like a separate phi inverse chart we reference to for phi or no?
There is, but I didn't like attach it here because like it on the if we would sorry if you need to the specific values of phi on the test, we will attach a chart. Otherwise, we'll probably ask you to leave it in terms of like phi inverse. How are we getting
I
the term 200 minus w over 2? Oh, okay. So the width has like, okay, this width is, it was from a different semester, so like their notation is slightly different. By their width, they mean like the whole thing here is w. So this means that if the whole thing is w and it's centered at 200, this one has to be like plus w over 2, and this one has to be minus w over 2. So those are like our bounds. Okay. And then like this turns out to be w is approximately 20 root 2 times phi inverse of 0 up like this. And if you're curious about the final answer, it turns out to be roughly 61.4 meters.
I think in the beginning you said like there was like a faster approach where you could just multiply by 2. Do you think you could like show that really quick as well or no?
Oh. So the idea behind that, it actually doesn't like save you that much time, but like you would just do one side of the interval. So like if this were a normal, you would just like get the probability between here and here. And then it would be like phi of like this right side. Minus 0.5 equals like 1 like 0. Half of 0.97.
Is there a reason why we don't do that for all standard normals since they're all symmetrical or no?
I mean, you can. I just did this way because it's like it follows my train of thinking better, but like you don't really have to.
I see. Okay, that makes sense.
All right. Okay, are there any questions? Yes, phi of A is the area to the left. So when we do like this minus this, oh, I'm gonna draw it out on the side. So if we do like phi of this minus phi of this, it's going to be this area minus this, whoops, like minus like this area. So all that's left is the middle part. Does that sort of make sense? Why do we do that just for a right half? It's because like you can always turn a two-tailed bound into one-tailed bound using the normal approximation. The thing we use is that phi of 0 is 1/2. But like it's like it just makes the algebra like one step nicer. It's not like conceptually different anyway. One more time, why it's 200 plus and minus w over 2. Okay, it's because the width is defined to be like the distance between the endpoints, which is different from what we see in class. And that's why it's going to be w over 2 on each side, and that's like plus or minus w over 2. Okay, how about this? When I publish the notes, I'll explain in more detail how the 1/2 bound works, but for now, I'm gonna move on. These will also be in the same thread where we post all the the sort of final week schedule things. How do we go from the algebraic expression of the CDF to the CDF of the normal thing? Oh, okay. So this thing itself is normal, which means that to turn it into normal, we want whether the normal is between this and this. And that would be like, this would be like probability that our cutoff is less than this minus the probability that it's less than like the other side. So to find the portion in the middle, we take this and we like scrub off the part that's like remaining here. So in the end, we get like a symmetrical thing. Okay. I think I'm going to move on to the last question then. Oops. Okay. So it says solve the previous problem, but I forgot to actually paste the previous problem. Just a second. I think Aaron also did this question in his review session. But like, it's a good example. Okay, so here there's like two parts, and I think this is a good example because like we can first try Chebyshev and then see how it turns into this CLT. So let's write down everything we know here. X has distribution plus on lambda. We don't know what lambda is, but we know that lambda is at most 10. I want to make a confidence interval for lambda that is of width 2. Here the width is like the actual width, which is like 1/2 of the distance between the two. All right. So first of all, our xi are going to be Poisson lambda. And we want to estimate this. So we use the fact that the expectation of a Poisson is like its parameter. So E of xi is going to be lambda. We can also use the variance, but like sum is a bit easier. So this means that if I call Sn the sum of all the xi's, then the expectation of like the sum is going to be n lambda. So here are like we see that to estimate lambda, we have to divide everything out by n. Okay. Oh, sorry. This is yeah. So here we see that it doesn't depend on n. Like we just want to estimate lambda, which doesn't have an n term in it. So we have to use the sort of averaged out estimator. Like it depends on the problem. Okay, sorry. To avoid confusion, I think I'll just write it as like Sn is the population mean, which is our estimator, and then expectation of Sn is going to be lambda. Okay, so we want a 95% confidence interval. Okay, so we want the chance that Sn lies within epsilon of lambda to be at least 95%. Like this is just saying in words. And with 2 means, well, we want to be within 2 of the correct epsilon. The correct lambda, sorry. And yeah. So for part 2, to turn into something that uses Chebyshev, we want to take the complement of both sides. Oops. Let's make this just so like it fits the Chebyshev version. Okay. Should it be 1 instead of 2? It depends on what we want like how they define width in this semester. And oh shoot. All right. It turns out they also used the width that was like literally the distance between the two endpoints. So if the whole thing is 2, we want each of these to be 1. Lambda plus 1, lambda minus 1. Okay. But like, don't worry, because on the test, if it's ambiguous, we'll say so. So now we can see that this is in the form of Chebyshev, and we can try to sort of fit it to what it is and solve. So by Chebyshev, plugging it in here. Yeah, 1, because it's 1 squared. And the variance of Sn is the sum of the variances, which is lambda over n. So, okay, I'll break it down a little bit. So this is going to be the variance of 1 over n times the summation of all the xi's. But because the xi's are independent, we can pull out this constant, 1 over n squared, times like the summation of all the variances of the xi's. So this would actually be n times the variance of an individual xi. Let's just say x1, because they're all the same. This cancels a little bit, and we get that this is going to be variance of x1 all over n, which by Poisson, like the variance is going to be, oops, is going to be lambda, so this turns into lambda over n. It should be greater than the second line. Yes, sorry. And now because we want this to be true, like this is true by Chebyshev, but we also want like this to be true. So the tighter bound is going to be lambda over n is going to be less than or equal to 0.05. Turning like this into the lambda thing. Oh, wait. Oh, how many hours? Sorry, I flipped it. Okay. Why is it less than 0.05? Oh, that's because we want our confidence interval to be 95%. So like probability that it lands within the interval is at least 95. So probability it lands outside is at most 0.05. And then so when we like do a little bit of algebra, it turns out that we want n to be at least lambda over 0.05. But we know that lambda is like upper bounded by like lambda is at most 10. So this is going to be at most 10 over 0.05, which is 10 times 20, which is 200. So we want the number of hours to be at least 200. All right. So this is like the Chebyshev version, which doesn't require any of the inverse norm CDF. Okay, we only have 4 minutes left, so I'll try to rush through what it would look like if we turned it into the CLT. To use CLT, we have to make Sn look like normal of 0 and 1. So this is going to be Sn minus expectation of Sn all over square root of variance of Sn. I'll simplify right here. And then variance of Sn is lambda over n. And this is going to look like normal of 0 and 1. So now if we have the same thing, like this probability stays the same. So we want probability of Sn minus lambda to be within 1 is going to be, it's going to be at most 0.05.
Should we be taking the square root of lambda over n or no?
You're right. Oh my gosh. Yeah, good catch.
Okay, thank you.
So now we have to like make this sort of look like this. So the rest is, well, pretty much just algebra.
Wait, sorry, do we not want it to be greater than 0.95, right? We want the
Oh.
absolute, yeah.
Okay. Divide out by square root of lambda over n. And now this middle thing is standard normal. So now we do the same like CDF thing, CDF of 1 over this. Uh, okay, so now we take the inverse CDF of both sides. Hmm. And are we trying to find the number of samples? Yeah, we're trying to find n. So n must be greater than this times lambda. Since lambda is at most 10, this means that like we can replace that with 10. And like this is it in terms of CDF. Did we subtract lambda from the 2 bounds? We subtracted lambda in the very beginning, so we didn't need to subtract it from each of these. Okay. And if you're curious about the numerical answer, this is roughly 10 times 1.96 squared. Could you explain how we define Sn to be the average and not the sum of all the xi's? Yeah, so it depends on like what you're trying to create a confidence interval for. Here, we're trying to create a confidence interval for lambda. And we notice that if we just take the sum, like the sum is gonna, like the expectation, the sum is gonna have an n in it. So to sort of have it in purely terms of lambda, we took the mean instead. Okay, are there any other questions? Okay, I'll stop the recording here. I'll stick around for a few more minutes.